Thanks a lot, Long, and thank you, Mingyao, as well, for this extremely kind, nice, and humbling introduction. I wish I were up to the merit of what Long was describing. Anyway, I thank you very much for inviting me to speak here today. It's a great pleasure for me. It is a topic that the topic of the workshop is a topic that I believe is a very interesting one, and it was a real pleasure. It is a real pleasure for me to be here and the privilege to talk about some results we've had with certain co-authors over the last few years on the direction of convergence and perhaps non-convergence in game-theoretic learning. By the way, I should check. Can you all see my screen? I guess it. I guess.
Yeah.
I hope
Yes, we can see it.
Okay, great. All right, thanks. So yeah, for this talk, I wanted to try to give you a sort of holistic perspective of the things I've learned or actually stolen from my interactions with my brilliant co-authors over the course of the last few years. On this topic, and this whole thing, this whole talk is about what outcomes can be stable or unstable under a large class of learning, no regret learning processes in games. And this is a work that we started with Bill Sandholm back in 2016, and then we continued with Christos Papadimitriou and Yorgos Pilyouras, always in continuous time at first, and then more recently with Agiliki Yanu, Manolis Vlatakis, and Cheng Yuan-Chu is when we shifted from a continuous time perspective, meaning from continuous time dynamics, to a more discrete time algorithmic framework. And so this distinction between continuous time dynamics and discrete time algorithms is going to play a major role in the talk. You see that it is actually split in two parts: learning in continuous time and discrete time, because there is a natural boundary between the two learning paradigms, and this is one of the things that I would like to explore. And I should also say that please, at any rate, at any point, don't hesitate to simply interrupt and ask a question as you have them. I think it's much better for everyone if we have, a lively talk, and then if I don't get to talk about one or two little details in the end, that's okay. It's much better to have a dialogue. All right, so just to give you some context, thankfully, thanks to the very interesting talks that came before my own, I don't have to motivate much of what I'm going to present. Already Ty's talk motivated how agents can interact in a fresh or a non-fresh environment, and this is precisely what I'm interested in. I'm interested in we're interested, I should say, rather, in very complicated environments where agents interact with one another. They do not necessarily cooperate because they do not even know who else is involved in the game. Think more or less of a typical commuting scenario where you try to get from home to work or the other way, and you have no idea who else is going to be on the road. You only could maybe guess some things about their aggregate behavior, and you would like to adapt to those. All right, so it is a common, players do interact in a common environment. This environment is not necessarily cooperative, not necessarily anti-cooperative, not necessarily purely competitive either, but it is a game. All right, and what we're trying to see is how, based on very little information, how agents can interact, what they can learn in this type of environment, and whether they can converge to some stable state or not. All right, so to start giving you the precise framework, if we look at the generic online decision process, then it always consists of it always consists of three basic parts. There is an agent who chooses an action receives a reward based on this action, and possibly gets some feedback. Now, depending on how what type of actions they choose, how the rewards are generated, and what type of feedback the agent gets, of course, we can have very, very many different types of learning processes. And the defining elements of such a learning process are, well, among others, the following. First of all, the time. How do epochs iterate, meaning is time continuous or discrete? Whether we are looking at a finite number of players or a continuous number of players, whether the players' actions are themselves continuous or finite, whether the reward mechanism is endogenous in the sense that rewards are only determined by what my actions and everyone else's actions are, or whether they are exogenous, meaning that they may be determined by outside conditions like nature or something else like the weather, which is not affected by our actions. And finally, by the type of feedback that is available to the agents, whether they are able to observe or predict each other's actions, their rewards, or the only information that they get is the payoff that they received, and that's that. All right. So, of course, as you can see, this is a huge, I mean, it is 1, 2, 3, 4, 5. So 2 to the 5, at least 2 to the 5 different learning frameworks here. So we're, of course, not going to talk about everything. We're going to, in this talk, as I said, we are going to consider both time, which is both continuous and or discrete. And we're going to focus on games with a finite number of players, a finite number of actions, and no exogenous influences on the player's behavior. So we're going to be in a purely game theoretic setting. And in terms of feedback, we're going to leave things open-ended. We're going to start with the simplest case where players do have a lot of information to work with. Maybe they know their entire payoff vector or something like that. And we will gradually go down to the case where they only have bandit payoff-based information and nothing else. All right. So this, as I said, is the basic framework that we will be studying. We have multiple agents, each with their individual objective. The payoffs are determined by the actions of all agents, and the iteration is done when agents receive their payoffs, they adjust their actions, and the process repeats. And what we would like to see here is whether this learning, whether the way that players adjust their actions actually leads to some stable or otherwise rational or rationalizable outcome. All right. So this is the basics. This is the basic skeleton of what we're going to try to study. And now the actual mathematical framework that we will consider. As I said, we're going to consider throughout the talk finite games. What does this mean? We have a finite set of players, a finite set of actions or pure strategies per player. And each player has their own payoff function for which we make no assumptions. So the payoff to a player depends on the actions of the individual player and the actions of all other players as a standard. What will be important throughout in terms of information is the payoff vector to each player, which is the vector of rewards that the player would have obtained if they had played a different action than the one that they chose. So basically, what this vector is for a given profile of the actions of all other agents, it collects all the rewards that I can get against the action profile of my opponents. All right, so this is just the vector of rewards with each component of the vector describing the reward of each of my actions against the fixed actions of my opponents. All right, so that's all there is to a finite game. I assume that more or less is that everyone is more or less familiar with this. So I'll move on. I'll move on to the mixed extension of a finite game, because I will not be assuming that players are only playing pure strategies. I will also assume that players can randomize, that they can play mixed strategies, which means that they can randomize over their action. So instead of always picking the same pure strategy, maybe they have a probability distribution with which they are choosing this a pure strategy at each stage. So if the mixed strategy of a player I is xi, which is a probability distribution on the simplex spanned by the player's pure strategies, then the mixed payoff of the ith player is simply the multilinear expectation over the corresponding pure payoffs. And likewise, the mixed payoff vector of player I is the vector of expected rewards that they would get for playing a given action against the mixed strategy profile of their opponents. All right, so both these two quantities are simply multilinear extension of these two quantities. Now, why am I insisting so much on these fundamentals? This is because there is going to be later a big degree of difference in terms of learning and in terms of the assumptions we need, whether players can only observe the action, the payoff of the action that they employed, the pure payoff vector of the profile corresponding to the profile of actions that were employed, or finally the mixed payoff vector of the function of the mixed strategies that were employed. All right, so obviously this is much less information than this. This is a scalar, this is a vector of dimension AI, and this, well, this is even more information because it needs the player to have some sort of information regarding not only the actual strategy, the actual actions chosen by the other players, but also relative to the mixed strategy with which they chose these actions. So this is considerably more information. And this is something that we will see has important implications in terms of learning what assumptions we'll be making. Not important for now. I just want to explain why I'm insisting in these fundamentals so early in the talk. All right, and give you a preview of what is to come. Now, oops, I see there was a problem in rendering the references. Sorry about that. Here, the standard solution concept that we have in game theory is that of a Nash equilibrium, which simply says that no player has an incentive to deviate from a chosen strategy if other players don't. All right, so we could have here either equilibria in mixed strategies, which is this, I should say, the Nash equilibrium formulation, I will consider directly the formulation in mixed strategies, which simply says what I said, that the payoff to a player following an equilibrium strategy is no less than the mixed payoff that they would get by deviating to another strategy. All right, and this says in terms of pure strategies that are supported, that the supported actions get a payoff which is strictly no less than the payoff of non-supported actions. Why am I saying this? Because geometrically, this means that certain components of the payoff vector at equilibrium will be no less than certain other components of the same vector. So the supported components will have will be greater than the non-supported ones, and this has an important geometric interpretation, namely the following. First of all, Nash, the payoff vector, the mixed payoff vector at equilibrium is always outwards pointing. All right, but now there are differences. If what are the differences? We need to make two cases, and this distinction will be very important for the sequel, whether the support of the equilibrium is a singleton or not. If it is a singleton, we say we have an equilibrium. Only one strategy is supported, so we have an equilibrium in pure strategies, so we say that it is a pure strategy equilibrium. And if we have a pure strategy equilibrium in which all these inequalities are strict, we say that we have a strict Nash equilibrium. All right, so what is the geometric image of all this? Is that in a mixed strategy equilibrium, payoffs are outward pointing, so you see that they are actually very delicate objects in the sense that outward pointing here means that any of these directions are not valid as equilibrium vectors. Why? Because they have a component which would induce an improvement along the simplex. So these are in general fragile objects. However, why? Because the normal cone to the equilibrium at this point in the simplex is very thin. It is simply a half line. Now, if the equilibrium is pure, then the normal cone is much bigger. So we have many more candidates, if you want, for equilibrium payoff vectors. And a strict equilibrium is one whose payoff vector lies exactly in the interior of this normal cone. Why am I making this distinction? Because this means that if I perturb the game a little bit, then this vector will be perturbed again by a little bit, but it will still be in the interior of the normal cone, which means that strict equilibria are geometrically, topologically, if you want, much more robust than their mixed non-strict counterparts. All right. And this topological distinction between mixed and non-strict equilibria, which is just geometric. I haven't talked at all about learning, but we will see that this robustness, this geometric robustness distinction will play a major role in the sequel, because we will end up having completely different results for mixed equilibria and completely different results for strict equilibria. All right. And I just want to I'm insisting so much on this exactly because I want to give you some, well, first of all, some idea of what is to come, and also to give you some geometric intuition of some of the results that are going to follow. All right. So with all this said and done, the main questions that I would like to answer in this talk is whether the game theoretic solution concepts that we talked about, Nash equilibrium, mixed, pure, strict, whatever, whether they are stable, whether they are attracting, whether learning dynamics converge to them globally, locally, or otherwise, and what other behaviors we can observe. All right. And just to manage everyone's expectations here, I should begin by saying that there is no, in contrast to convex optimization, which is which has sort of spoiled us with all the super powerful global convergence results that we have there. In games, there is no such thing. There are, I apologize for this. It seems that we have a bug with the references. This is a result by Hart and Mascolel in 03, that there is a result that says that there exists no uncoupled dynamics which guarantee convergence to Nash equilibrium in all games. And by uncoupled means that the agility of a player's strategies only depends on that player's payoffs, not also explicitly on the payoffs of all other players. All right, so why am I saying this? Because we should not expect some learning, which is by necessity a distributed process, to converge globally to equilibrium in all games. This is too much to expect. So by necessity, we will have to temper our expectations and work with convergence results that are of a bit more restricted applicability. All right, so that's the intro. That's all I wanted to say before I start with the results. I don't know if there are any questions in the chat so far. All right.
So I have a question.
Yes.
I probably miss your exact definition of the pure strategy Nash equilibrium. Is that the equilibrium concept guaranteed to exist?
No, definitely not.
Okay.
No, okay. Definitely not. It is whether it exists or not. This depends on the game. In some games it exists. In some games it doesn't.
I see. Yeah. Okay. Thanks.
All right. Yes. I don't know if there are any other questions.
Yeah. So in the theorem, what do you mean by all games here? So yeah, what type of games?
I mean, we're always in the context of finite games, all right, or rather mixed extension of finite games. And to give a more specific a more specific statement to this. In the original paper by Hart and Mascolel, they were looking at continuous time dynamics, and they showed that there exists a game such that every uncoupled dynamics would be asymptotically unstable around the game's unique equilibrium.
Okay, thanks.
All right. Know if there are any more questions. Okay, so let me go on then. Yeah. So again, as I said, now we're gonna the rest of the talk is gonna be made out of two parts. First, learning in continuous time, which will set the stage more or less, and then we will move on to learning in discrete time, which is the more algorithmic and thus perhaps more interesting from an ML point of view, or from a more computer science point of view. All right, but still, this is important because it will give us some intuition of what type of results we can get. Oh, whoops! I'm sorry about that. That's a mistake. All right. So when we're talking about learning in continuous time, we mean we have a finite game gamma, then time is continuous, and at each point in time, players choose a mixed strategy. They encounter some payoff vector based on this mixed strategy. And I will be assuming for this part of the talk that the players observe their entire mixed payoff vector so that I can write easily a dynamical system and not have to worry about information and all that. All right. This is an important assumption, but one that we will relax later. Okay, so as a starting point and to warm us up, I will consider a stimulus, a so-called stimulus response model, which is known in the literature as learning with exponential weights or sometimes multiplicative weights. And the idea for this is very simple. Each player builds a score variable for each of their strategies by aggregating the payoff that this strategy has given the player over time. All right, so they look at the payoff that this strategy gave at time t, and then they integrate it over the entire horizon, and this is what they call the score of said strategy at time t. All right, and what do they do with that? Well, obviously you want to employ strategies with better scores, but in order to avoid being basically locked into a strategy prematurely, it is good to also have some exploration. So instead of just playing the strategy with the highest score, players simply assign exponentially more probability to the strategy with the highest score. So what this means is that they play a strategy alpha with probability which is exponentially proportional to the score of said strategy. Okay. Now, if you normalize, this is the precise rule that they are using. And if you differentiate this in order to try to obtain a dynamical system which describes how the player's mixed strategies evolve over time, you get what is known as the replicator dynamics. All right, this equation is very well known in the literature, and it has been studied early on by biologists and all that. Now, what I'm interested in, however, is this part of the scheme, because in essence, what we're doing is, instead of picking the strategy with the highest score, what we're doing is we are regularizing this selection problem. In the case of the exponential map, we can show that if you regularize this problem by adding the negative entropy, then what you get is exactly the exponential selection, the exponential action selector that I talked about before. All right. So, so what this means is that this type of exponential learning dynamics can be seen as sort of following or choosing well, not the leader, not the action with the highest score, but the regularized leader, meaning the action with the highest score modulo regularization. And of course, one can ask, why use the entropy here when you can use another regularizer, such as, for example, the Euclidean regularizer or what have you. Well, you can do this. You can most definitely do this. The general framework that we will consider is precisely this, where you are regularizing here with some arbitrary function, and because of this regularization, we will call this dynamics follow the regularized leader. Now, to be clear, this is not the name that I came up with. The name goes back to Schwartz and his co-authors, but in continuous time, in a game theoretic setting, this is more or less the dynamical system that we get. And I put a C here to remember that we are in continuous time. All right. Now, we've already seen an example of this. The replicator dynamics is an example of an FTRL dynamics. Another example comes if we do this quadratic Euclidean regularization, in which case, well, the corresponding action selector is no longer this exponential, this logic choice map, but the Euclidean projector. And what you end up with is a version of the projection dynamics where instead of projecting gradients, as we do in optimization, we are projecting payoff vectors. All right. So, okay, we've defined the class of dynamics that we'll study, understudy. What do they look like? Well, let me show you some pictures to get some intuition. The picture I'm showing you are of two-player games to begin with. Here is the mixed strategy of one player. Here's the mixed strategy of another player. And all these points here are different initial conditions. And the trajectories show you the evolution of the mixed strategies over time and where they converge. So here, all these trajectories converge to these points, which are equilibria in this case. All right. So this is what the replicator dynamics look like in a congestion game, a hugely simplified version of the routing problem that I talked in the beginning when you're trying to deal with commuting in an urban metropolitan area. All right. In another game, they could be somewhat inverted. So if instead of a congestion game, we take a coordination game like Battle of the Sexes, then the image is inverted here. If we take a zero-sum game like matching pennies, then we have something quite different because we have an equilibrium in the middle and then all these trajectories cycling around the equilibrium. And if we take another game like a Prisoner's Dilemma, where there we have each player has a dominated strategy and everything converges to a single point. All right. Now, in 2x2 games, that's it. Up to conjugation, so up to isomorphism, basically, you can't have at least generically, you can't have any other behavior. That's all you can have. All right. So these four portraits, depending on how you count them, is all that you can have in 2x2 games. But then, of course, 2x2 games are very nice to draw pictures, but they are by far the simplest thing that we can consider. And if we start moving even just by adding just a third player with two actions, then the profiles start getting increasingly complicated. Like we could have completely non-convergent behavior like here, or we could have convergent behavior, but you see that again, the convergence is still at the boundary. Or we could have a mixture of cycles and convergent behavior. So things start getting very complicated. And this is only in the class of the replicator dynamics. If I consider the projection dynamics, then we see that we have also some geometrically different dynamics even in familiar games. So if we look at matching pennies, what we see happens in the case of the projection dynamics, we see that trajectories may enter the boundary at a finite time, then exit the boundary, they enter the boundary again, exit it, enter it, exit it, and so on and so forth. Whereas in the replicator dynamics, things like that don't happen. All right. So again, I could keep showing you pictures, but that's not what I want to do. I want to discuss at least what are the major conclusions that we can draw, at least for this entire class of FTRL dynamics, and what conclusion we can draw relative at least to Nash equilibrium. And well, The first basic conclusion that we can draw, which is a very basic one, but without it we can't really go anywhere, is that if if a point is a Nash equilibrium, then it is stationary under these dynamics, meaning that if we start at Nash equilibrium, then we will always stay at a Nash equilibrium. On the contrary, however, rather the converse of this is not true, and we have already seen an example of this. Oops, I'm sorry. For example, if you look at this game, well, these points here are stationary points of the dynamics, but they are not Nash equilibrium. So when we consider learning, we already from the first step we have an obstacle to overcome, namely that that Nash equilibria aren't the only stationary points of learning. So this is difficult. This is already a big difficulty that we have to overcome. But then, so we need to try to distinguish rather between stationary points, and one way to do this is to see whether some of them are stable or not. So stable, what does it mean? We have the notion of Lyapunov stability in dynamical system, which tells you that a point is stable if all trajectories that start close enough to this point remain close enough to this point. So there are no trajectories that escape if you start close enough. And then you have the notion of asymptotic stability, which combines the notion of stability with that of attraction, which means simply that trajectories that start close enough to the point in question eventually converge to it. All right, so asymptotic stability, this notion over here is exactly what we would like Nash equilibria to have, because this means that at least locally they are both stable, so no trajectories escape from them, and they are attractive, meaning that they can actually attract trajectories. And well, this is perhaps this is a result that encompasses all these notions, and which tells you, which is a general result for all FTRL type dynamics, and it says the following. First of all, as we already saw, if Nash equilibria are stationary, we've already seen this. But then what we also have is that if a trajectory converges to some point, then that point must be a Nash equilibrium. All right. So in a sense, the only possible limit points, or the only possible limit points, and I mean, of non-stationary trajectories of all FTRL dynamics are Nash equilibria. So this at least is very good news. More to the point, we have that if a point is stable, then it is a Nash equilibrium. And if we also consider the property of attractivity, then we have the following very important equivalence to the effect that, well, strict Nash equilibria are asymptotically stable, meaning that they are stable and attracting, and they are the only points that can be asymptotically stable. All right. So this is a very important element to keep in mind, because this tells you that the only stable limit points of a regularized learning process are strict Nash equilibria. Mixed Nash equilibria, boundary Nash equilibria, they cannot be stable, they cannot be attracting rather under an FTRL type dynamic. All right. And
sorry, can I have a question? Yes. Number two. So it means that if there exists a convergence path, then it is a Nash equilibrium. Does it mean that way, or did I misunderstand something?
Exactly.
Okay,
exactly.
Thank you.
So any more questions on this? Because actually this is the main theorem I wanted to talk about in the continuous time case.
But point two, like you saw in a picture that there's a stationary point that is not Nash equilibrium. Does it contradict to two?
But there's no convergence to there.
You see, right? Exactly.
There's no convergence to there. Okay.
You see, there is no trajectory which actually converges here.
Okay.
If there were even a single trajectory that converges to this, then that point would have to be a Nash equilibrium. All right, and not only that, what I'm saying here is that no other stationary point, and not even this point here in the middle, which is a Nash equilibrium, well, this guy over here cannot be asymptotically stable. Only strict equilibria, only these two strict equilibria can be asymptotically stable. All right. All right. Are there any more questions here? All right. So then I'll move on directly. I'm gonna skip some slides that that I had, because I want to focus more on the algorithmic side of things, and I want to see what happens now if, instead of having these smooth, very nicely evolving dynamical systems, we work in a much coarser world, well, in discrete time, where we have potentially much less information at our disposal. So, well, in the ideal case, we can still observe the mixed payoff vector, but maybe we only have realization-based feedback. So this means that we can only observe our pure payoff vector, which in practice means that given the actions of my opponents, I can infer what I would have obtained by playing another pure strategy than the one I played. These are the information requirements for observing a pure payoff vector. Or the hardest case of all, where the only information that I have is the payoff that I got from the action that I played, and that's that. All right. So I want to start treating cases like that in discrete time, so that we have implementable algorithms. And well, what is crucial here, especially for the last part, which is how to go from a scalar of information, meaning the actual payoff, back to a vector of information. All right. So here, thankfully, the very smart people in the bandit literature, in the bandit community, have come up with a way to do this, which is the importance weighted estimator, which is something which is known for several decades now, and which simply constructs a very coarse estimator of actions that were not employed. What it does, it simply says, sets them equal. You don't know nothing about them, so set them equal to 0. But for the action that you actually played, well, don't use what you actually obtained as an estimator, but rather scale it, weigh it down by the probability with which you chose this action. All right. So this is the importance weighted estimator, and its key properties, perhaps its most important property is that it is unbiased, meaning that on average, this gives a true estimation of the player's mixed payoff vectors. All right. Of course, the key disadvantage is that, well, we have a sort of a bias variance dilemma, in the sense that we have no bias, yes, which is good, but we have potentially unbounded variance, which is bad. And we will see that this plays a role in the sequel. Now, to integrate all these different models in a single one, well, a convenient way to do this is to use what is known as a stochastic first-order oracle model, which simply assumes that we are given, or that we are able to reconstruct, some random vector, which is the mixed payoff vector plus some random noise plus some bias, depending on the estimation process that we are using. All right. So if we are able to observe the mixed payoff vectors, then of course we have no noise, no bias. If we are observing the pure payoff vectors, then we have no bias but noise. And if we are using a payoff-based estimator, then we still have no bias, but we have much bigger noise. All right. And if I start to see what happens when I run the discrete time analog of the exponential learning dynamics, which is the exponential weights algorithm, well, this is the algorithm that I get. Again, it is the same, it has the same idea. I upgrade the score of a strategy based on the information that I get. I aggregate them, and then I play a strategy with probability which is exponentially proportional to its score. And then the question is, what type of results can I get? Again, of course, here, just to reiterate, it is very important to keep in mind that the difficulty of the learning is hidden to a great extent in the estimator that I put here. As I said, if we have mixed payoff vectors, then this is perfect information. This is the best case. If we have only pure payoff vector observations where things are worse but still manageable, if we only have realized payoffs, then we need to use importance weighted estimation. Maybe we need to introduce some explicit exploration in order to control the variance, etc., etc., etc. What I'm trying to get at is that now we're in a position to state the complete framework of algorithms that we'll consider, which consists of the following dimensions. First dimension has to do with all the hypotheses, all the assumptions that we used for the oracle, for the type of payoff signal that enters the player's learning process. And the second has to do with the action selector mechanism, which in the exponential weight mechanism, exponential weight algorithm was the logit map. More generally, it could be any regularized map, as we saw in the first part of the talk for continuous type dynamics. All right, so these are the two dimensions: the type of regularization we use and the payoff signal that is entering the process. All right, and all the results that I'm going to state will be on this general class of algorithms. All right, so I don't have to mention any more examples. I will just show some pictures again in the previous games that we saw. What happens when we run let's say these discrete time algorithms? And what you can see is that at least when we have these convergent type profiles, well, of course, we're doing a random walk here, and a somewhat bizarre one might say, but eventually we end up converging to what the continuous time dynamics converge to. The same is true in this case. Now, if we have a non-convergent profile like in matching pennies, where we had these cycling profiles, well, there things are different, because you see that we have basically a random process which goes around and around and basically covers the entire space. So it is we don't have this very nice foliation structure into nice periodic orbits. We have basically this recurrent process that goes all over the place. All right, so here the behavior of the continuous time dynamics and the discrete time dynamics can be quite different. But again, if we go back to the prisoner dilemma where we have a convergent profile, we see that we maintain the same convergence properties. So far, at least experiments would suggest that at least in everything that has to do with the convergence aspects of our continuous time results, well, hopefully this should continue to hold. And this is actually indeed the case. I will skip some definitions which are the mathematical, the formal analog of how we need to define the notions of stability and asymptotic stability in a discrete time context, in a discrete time probabilistic context. There are some complications that have to be addressed precisely because we are in a more, well, complicated setting. But I don't want to insist so much on this. When I say stochastically asymptotically stable, you just need to think asymptotically stable with high probability, and you won't go wrong with that. And I just want to focus on the result, on the type of results that we can get, and which are the following. Well, as we said, we would like to compare somehow the convergence properties, the convergence profile of the continuous time dynamics with those of the discrete time dynamics. And in order to do this, we actually need to make some assumptions about the various errors and the various parameters that are entering the discrete time algorithm that we studied. And these These assumptions can be quite complicated in general. In the case of FDGL methods with the stochastic first-order oracle feedback, well, they can be simplified considerably if we consider a step size, a learning rate sequence, which is of the order, which is of the type 1/n to some power. And in that case, we can check that all the models that I've presented so far, including mixed payoff vector, pure payoff vector, importance weighted estimation with explicit exploration, optimistic exponential weights that I briefly mentioned, all those models satisfy these conditions. All right. So thankfully, these complicated conditions that we need in order to have the bridge between continuous and discrete time are satisfied by all the models that we've discussed so far. And under these conditions, what we can show is the following, that again, in discrete time with this stochasticity, this inherent uncertainty in the players' payoffs and their observation and the information that they receive, well, we still have the following results. First, if a trajectory, if a point emerges as the limit of some sequence of play, then that point has to be a Nash equilibrium. It can't be anything else. Moreover, if a point is stochastically stable, it has to be a Nash equilibrium again. And not only this, but we still have the same equivalence between points that are stochastically asymptotically stable and strict Nash equilibria. So strict Nash equilibria are stochastically asymptotically stable, meaning that they are stable and interacting with arbitrarily high probability, and they are the only points that have this property in finite games. All right. We can also get perhaps more results about congestion games or zero-sum games, but I don't want to get into this level of detail. I want to stop basically here and examine and see if we can get something more about the rate of convergence, because it turns out that we can actually do get some rates of convergence for this type of processes. And what we can show is that if X is, if we have a strict Nash equilibrium, which, as we said, is stable and interacting with arbitrarily high probability, then for any of these trajectories that converges to it, the rate of convergence will be controlled by a function which turns out to be the, I mean, I know it's weird, but it is what it is. It is the inverse of the derivative of the regularizer map. Concretely, what does this mean? If the regularizer is the negative entropy, which is what we have in the case of the exponential weight dynamics and the exponential weight algorithm, then we have geometric convergence in the effective running time of the sequence, meaning in the sum of the step sizes. So in general, if you run it, let's say with gamma n, which is 1/n to the p, this will be a rate of this form. All right. Perhaps more interestingly, and this is where the analysis, where game theory actually and regret minimization give wildly different predictions or lessons. In regret minimization, we know that exponential weights are basically optimal in terms of regret guarantees, and that if we run things with a Euclidean regularizer, then we get highly suboptimal regret bounds. However, in a game theoretic setting, this is not so. In a game theoretic setting, if we use a Euclidean regularizer, then we don't get convergence at the geometric rate. We get something much stronger. We get convergence in a finite number of iterations, almost surely. All right. And well, that's what.
Sorry, can I ask a question? So when you mean like,
yes.
if convergence in finite number of iteration, it means that by the end of the, let's say, n number of iteration, by the end of each, you get exactly
yes.
the equilibrium point?
Exactly. I mean precisely that there exists some possibly random n0 such that xn is exactly equal to x star for all n greater than or equal to n0.
Oh, nice. Okay, thank you.
All right. Yeah.
Is there any high-level intuition on why this is true?
There is, and this is actually the reason that I showed you this this picture over here. What happens with all these learning processes is that the aggregation of scores actually takes part, well, not in the simplex. The scores of the strategies are not constrained to live in the simplex. They live in a dual, they live in a somewhat dual unconstrained space, and they evolve. And what happens is that, well, convergence, what does it mean if we look at this dual process? Well, we have convergence in the primal space, in the simplex, whenever this image, whenever this evolution of scores actually hits the inverse image of the polar cone, of this normal cone. Okay, and so what happens is that the score process evolves in this dual region, and then sometimes because there is a consistent drift pulling it towards this normal cone, what it does is it starts traveling inside the polar this normal cone, but the corresponding image that we see in the corresponding image that we see in the primal space is something like that.
Oh,
why? Because everything that keeps evolving here, everything that is here under the projection dynamics is mapped to a single point. All right, and this is why the projection dynamics, which are very aggressive and thus very exploitable in a regret minimization case, in a game theoretic setting, they end up giving convergence in a finite number of iterations. All right.
I see. Very interesting. Thanks.
Thanks for the question. It's a very good question, and it was this image that I showed you was actually how we were able to somehow interpret and make sense of this result in the end. Anyway, that's basically all I had to say. Perhaps if I have a finishing phrase, what I want to say is that in continuous time we have a very smooth, we have some very robust equivalences, but which start being degraded, let's say, when we go to discrete time in a discrete time stochastic setting, because there many things become dependent on the feedback and noise, but still one key element that we can maintain here is the equivalence between asymptotic stability and strict Nash equilibria, which tells us that strict Nash equilibria are in a sense have like a favorable position in terms of learning, because they are the only stable limit points thereof, at least with high probability. And well, of course, there are many open questions that remain, as in regard to, for example, non-singleton attractors or other issues that come into implementations of discrete of learning algorithms, such as robustness to delays, corruption, asynchronicities, and whatnot. But again, this is perhaps for a different talk. So thank you very much for your attention and your patience.
Thank you very much. Any questions from the audience?
Yes, I have a question related to learning in discrete. When you said that zero-sum game doesn't lead to point carry recursion, from what I understanding correct, if I understand correctly, from asymptotic stability equivalent to strict equilibrium, just mean that you have lower conversion, right? So when you don't start with a very close point to the equilibrium, strict equilibrium point, we mean that it can lead to diversion, right? It doesn't converge. Is that correct? So like yes. In zero-sum game, you still can have point carry recursion because you don't start with the closely related to strict equilibrium point.
All right. So, very good question. Let me first say the following: that in discrete time and especially in a stochastic setting, the notion of Poincaré recurrence, unfortunately, does not really make sense because with probability 1, no system would be Poincaré recurrent. But this is not I believe the crux of the question. Yes, it is true that in zero sum games you can have well, rather, let me say this: if you have zero sum games with a strict Nash equilibrium, that strict Nash equilibrium must be if you have zero sum games with a strict Nash equilibrium, that strict Nash equilibrium remains locally asymptotically stable. You won't have an interior Nash equilibrium in that case. If you only have an interior Nash equilibrium, then of course, as you said, the theorem doesn't say whether you have convergence or not, and in fact, you do not have convergence. Your processes follow a random walk which is recurrent, not Poincaré recurrent, but recurrent over the entire region. So you wouldn't have convergence in that case.
Yes, yeah, okay, I get it now. And besides,
I'm not sure if I answered your questions though. I answered to the best of my understanding. If I didn't, please let me know so I can clarify.
Yes, you answer my question. So for global convergence, so the result that you provide only be true for potential game. You make congestion game. I anticipate that it's potential game. So only for potential game, right? So we have global conversion. Okay.
Yes. There could be some other classes of games where you could have global convergence results, like supermodular games or 2/n games, some 2/n games possible, but you need some structural conditions on the game to get global convergence.
Okay. Okay. Thank you. Thanks a lot. Yes. Fantastic talk. Thank you.
Thank you.
We have time for maybe a quick question.
So I have a general question. What do you think is the connection between the continuous time learning and discrete time learning? Is it there's an intrinsic gap between the results of the two?
Very, very good question. I'm not sure if I'm citing it here. I'm not. There is a line of very important works called the stochastic approximation and the ordinary differential equation method of stochastic approximation, which are works by Michel Benaim, Vivek Borkar, and earlier by Kushner and Yin. And all these works have focused on precisely this question that you say, to connect the long-term behavior of the continuous time dynamical system to its discretization. I would say that the general answer, the most general answer that I can give you is that robust convergence results, like for convergence to attractors or convergence or asymptotic stability, these are things that once you have in continuous time, they are maintained in discrete time as well under assumptions of differing strength. However, results on recurrence, non-convergence results like on Poincaré recurrence, these are much more fragile and they are easily destroyed, and they do not really hold in discrete time, and they cannot be ported. But this is a very deep question, and one which you might want. I would very strongly recommend the monograph of Michel Benaim for this.
I see. Yeah, I would check out that. Thanks a lot.
Yes, thank you very much. I think we run out of time now, so I just would like to take the time to thank Panayotis again. It was a fantastic talk. Personally, I think I learned a lot. It was very deep presentation, really talk. I will send you an email with my personal questions as well, so you can expect something from me.
Thank you so much for having me and for putting together such a great workshop.
Yes, and yeah, then please, just all of you, please stay with us, because we have 2 more fantastic talks coming up. One is about the Turing completeness of no regret learning. The other one is about how to exploit learners. Yes, so see you around.
Thank you.